So, to really understand the fundamentals of ECG, you must first understand the electrical activity of the heart. Right. So, let's talk about the electrical activity in the myocardial cells. Here, I draw three ventricular myocardial cells, and we see what is the electrical activity normally in these cells. And we see how the electrical activity goes through that. Right. Then, we'll discuss how that electrical activity can be eventually translated into ECG pattern. Let's suppose that, right now, these myocardial cells are not stimulated. They are unstimulated. There is no action potential passing through them. So, we say these myocardial cells are resting. If the cell is electrically resting, it must have resting membrane potential now. What is the resting membrane potential? Resting membrane potential is the electrical voltage difference between the inside of the membrane and outside of the membrane. Normally, resting cells of the ventricular myocardium are electrically negative inside. For example, the resting membrane potential is minus 90 millivolts in a resting cell. When I say this, myocardial cell has minus 90 millivolts resting membrane potential, I mean that in the resting condition, this myocardial cell has its membrane internally polarized negatively. Now, what really happens is that as soon as the cell is stimulated, its resting membrane potential will reach the threshold. As I said, resting membrane potential is minus 90 millivolts. If we stimulate the cell, then some cations will come in, some positive charges will come in. Let's suppose that we bring some sodium or calcium ions in. If we bring some electropositive ions in, what will happen is that this electropositivity, which is coming into the cell after the stimulation, this will take the resting membrane potential towards a less negative value because these positive charges will neutralize the electronegativity. So what really happens, as soon as positive charges are coming in, resting membrane potential is becoming less negative. For example, it becomes minus 80, and then it becomes minus 70 millivolts, moves towards the threshold potential. And let's suppose in this cell, threshold potential is minus 70. Here, threshold potential is a potential at which the membrane of this cell will suddenly open voltage-gated sodium channels. Right now, these channels are off. These channels are not working. But as soon as you stimulate the cell and some cations are coming in, resting membrane potential starts moving towards threshold. As soon as it touches the threshold, voltage-gated sodium channels open up. As soon as voltage-gated sodium channels open in the cell membrane, a lot of sodium comes in. Because normally sodium is more outside the cell. As soon as the resting membrane potential goes to the threshold voltage, then voltage-sensitive sodium channels open and a lot of sodium comes in. This sodium, as it is rapidly coming into the cell, is progressively neutralizing the electronegativity and the threshold potential, which was minus 70, it will become minus 60, minus 50, minus 40, and eventually it will become 0. It means as more and more sodium is coming in, this membrane potential is progressively going towards a positive value. Initially, it is losing the electronegativity, and eventually it may become positive. So what has happened is that once the voltage-gated sodium channels open, a lot of sodium comes in. This movement of sodium inside neutralizes the resting membrane potential and takes it towards electropositivity, and we say the membrane which was previously negatively polarized, it has lost its negative polarity. Or we simply say the membrane is depolarized. The next electrical event is the depolarization-sensitive calcium channels and potassium channels both start opening. And you must be knowing, normal healthy cell is very, very rich in potassium intracellularly. Potassium is normally more as compared to the extracellular potassium, and extracellular calcium is normally more as compared to intracellular calcium. Previously, the cell underwent a lot of sodium influx that led to the phenomenon of depolarization. Then, depolarization-sensitive calcium channels and potassium channels opened. When potassium channels opened, I told you, inside of the cell is very rich in potassium, so potassium will start leaking outward. There is efflux of potassium. It means the cell starts losing cations. It comes towards electronegativity, but as soon as it is around zero, voltage calcium channels also open. For a very short time, potassium keeps on moving out and calcium keeps on moving in. Means for a brief duration, potassium as positive charges are lost and calcium as positive charges are gained. So it means for a brief duration, cations are lost as potassium as well as cations are gained as calcium. So loss and gain of calcium balances the potential. So what really happens is that as potassium is being lost, at the same time calcium is being gained, so there is no net change in potential. But as time passes by, calcium channels start closing. But as time passes by, potassium channels become more and more active. So what is the result that by this time, no more calcium is coming in, but because potassium channels have become more active, so potassium losses become very, very heavy. There's a heavy potassium efflux, and as more and more potassium is going out, it means more and more positive charges are going out. Means the cell will again start developing electronegativity, because the cell is losing the positive potassium. So when potassium keeps on moving out, what really happens is that the cells, due to loss of positively charged potassium, become progressively electronegative, and potassium is progressively being lost. Potassium is being lost until the membrane potential again becomes minus 90 millivolts. So what really happens is that electrically, the membrane has come back to its negative polarization. If the membrane has come back to its negative polarization, it means the membrane is repolarized. Due to potassium efflux, the membrane has gone to the phenomenon of repolarization.